Every single day, information just flashes across the globe in an instant. It feels like total magic, right? But it's actually one of the most incredible high-speed systems ever built. So today, we're going to pull back the curtain and demystify the magic behind a single click.
I mean, really think about it for a second. You do this all the time. You type in a web address, you hit enter, and bam, a page appears, maybe from halfway around the world. But what is that invisible, high-speed chase that happens in that split second? Well, let's find out.
To really get it, we're going to trace the entire path of one single request. We're going to follow it right from your computer, across this vast network of the internet, all the way to a server, and then all the way back. Let's start the journey. Okay, so the very first problem your computer has to solve is pretty simple. Where am I even going? You've given it a name, like wikipedia.org, but the internet doesn't really work with names. It works with numbers. So the first step is always to find the right address.
And this is where something called the Domain Name System, or DNS, comes in. Just think of it as the internet's massive, globally distributed phone book. Its entire job is to translate the name you can remember into the number that the network can actually use. And this lookup? It's this lightning-fast chain reaction of requests. Your computer asks a local resolver, which might ask a root server, which then points to, say, a .org server, which then finds the final server holding the address. And this entire global conversation happens in just milliseconds. I mean, literally faster than you can blink.
So, just like that, in a flash, DNS has found the right number. Now your computer has the one crucial piece of information it needs to actually start the journey, the digital address of its destination.
And this right here is exactly why DNS is so essential. On the left, that's what we type. On the right, that's what computers need, a string of numbers called an IP address. Imagine if we didn't have this translation. We'd all have to memorize impossibly long numbers for every single website we visit. No thank you. An IP address, or Internet Protocol address, it works just like a postal address for a house. Every single device connected to the internet, your laptop, the server hosting the website, everything has a unique one. It's the definitive send-to address for all internet traffic.
All right, so now we have the address. We can finally send our message. But here's the really clever part. We don't send it all in one big chunk. Oh no, the internet has a much more efficient way of doing things. Your request actually gets broken down into these tiny, standardized pieces called data packets. A good way to think about it is like tearing a very long letter into thousands of little postcards. This makes the whole system way more resilient, and it lets lots of different users' data travel along the same lines at the same time. And each one of these digital postcards is meticulously labeled. Every single packet has the from and to addresses, that's the source and destination IPs. It's got a sequence number so they can all be put back together in the right order. And of course, it has the actual piece of the message it's carrying, which we call the payload. Now, this quote highlights a really cool detail. The IP address we've been talking about, that's the final destination. But there's another more local address that guides the packet to just the very next device on its journey. So think of it like the difference between the final street address on a package and the specific directions for making the next turn. And the devices that manage this whole journey, those are routers. They're basically the traffic cops of the internet. A packet arrives, the router reads its final destination IP address. It instantly checks its map of the internet and then sends that packet along the most efficient path to the next router, getting it one hop closer to where it needs to go. So let's recap. We've broken our message into thousands of tiny postcards, and we've sent them zipping across the globe through dozens of these traffic cops. But what happens if one gets lost? Or what if they arrive all mixed up? How does anything ever get there intact? Well, this is where the Transmission Control Protocol, or TCP, comes into play. You can think of TCP as the internet's quality control manager. It is responsible for making sure every single packet arrives safely, checking for errors, and putting them all back together in the correct order on the other side. It's kind of like certified mail, TCP doesn't just send the postcards out and hope for the best. Nope. It waits for a confirmation receipt for every single one. If a packet goes missing, TCP notices it's gone and just requests a resend. It's what guarantees reliability in a system that could otherwise be completely chaotic. Now, this incredible, super reliable system was built on a foundation that, believe it or not, is now showing its age. The very addresses that make this whole thing work, well, we're running out of them.
See, the original system, which is known as IPv4, had a capacity of about 4.3 billion unique addresses. Back in the 1970s, that seemed like an infinite number. But today, with phones, laptops, smartwatches, even our refrigerators all needing an address, we have basically used them all up. So the internet had to evolve. It had to upgrade from IPv4 to IPv6. And the scare of this change is almost impossible to wrap your head around. We went from a 32-bit address to a 128-bit one. Now, that's not 4 times more addresses. It is an astronomically larger number. It's enough for trillions upon trillions of devices. And on top of that, IPv6 comes with other critical upgrades, like having security built right in. To put it simply, IPv6 is the future. It is what makes the whole Internet of Things even possible. It was designed from the ground up to handle this explosion of devices that all need to connect to the network, making sure the internet can keep on growing for, well, a very long time. And that leaves us with a really fascinating final thought. We've just solved the problem of running out of digital real estate pretty much forever. So what happens when every light bulb, every car, every medical sensor can have its own unique, permanent address on the global network? What kind of new possibilities does that unlock? That is the future this invisible journey is taking us all toward.